Hi, my name is Chris Tully. I'm glad to be here, part of the Neutrinos from Home conference to talk on the current and future prospects for the Ptolemy experiment. Ptolemy is an experiment aimed at detecting the relic neutrinos from the Big Bang. Neutrinos are, to some extent, the unsung heroes of the universe. They have a very pivotal role in shaping the properties of the present-day universe. We believe that they decoupled from matter at roughly 1 second after the Big Bang, and at that time were roughly half of the total energy density of the universe. But during that um, early period in which we have observables, such as the relative abundance of light isotopes, neutrino relativistic energy density is influencing the period, for instance, of the photodisintegration of deuterium, which is one of the periods of it allows for the onset of nucleosynthesis. Similarly, at 75,000 years after the Big Bang, neutrinos are still an important energy density, setting the period of matter radiation equality, which has, for instance, a great influence on the start of acoustical waves in the relativistic electron-photon baryon plasma, and therefore the growth of anisotropies. And then in the late universe, neutrinos are there through their weak interactions in solar cooling, and their high flux influence on the supernova dynamics. Um, and so if we look at the range of beautiful experiments that we're doing in the field of neutrinos, the Big Bang neutrinos are by far the lowest energy bin of a spectrum of measurements that we hope to make. And you might ask, why concentrate on this area? Well, the neutrinos are, relatively difficult to interact with. They have been with us throughout the history of the universe, and it could be that they have an important story to tell, perhaps through their interactions with the dark sector. We just really don't know until we take a look. What we do know is that if we link the neutrinos to the total sort of entropy in the universe from measuring of the cosmic microwave radiation, we can sort of backtrack through matter radiation equality to the period in which neutrinos decoupled, which is believed to be before electron-positron recombination. Is a beautiful plot from the paper of Dickey, Peoples, Rowan, Wilkinson, 1965, already indicating point in which neutrinos are believed to decouple from the rest of matter. So from that, we get a prediction for the total number of neutrino plus antineutrino per species of roughly 112 neutrinos per cubic centimeter in the present day. We know what their relative momentum spectrum is compared to the photons because of this model of when they decoupled. We know that they had a very important role, or if you will, the timing of their decoupling is critical from the neutron to proton ratio. And they also have an important footprint that's uniquely placed upon them because they were decoupled at relativistic energy. So they have relativistic Fermi-Dirac statistics in terms of the density of states in the current universe. So the neutrinos potentially could have had an important dynamics in even the period, let's say, of the lambda CDM desert between Big Bang nucleosynthesis and the recombination period of relativistic plasma. This is one prediction of rethermalization of neutrinos with the dark sector. And the reason I point out this one among the different ideas people have is that it's about the concept of the Ptolemy. The name of the experiment is that although we have a numerically accurate description of the universe like Ptolemy had for instance, prediction of a total solar eclipse in North America recently, there could be a conceptually important critical role that neutrinos play that we would only get from sort of probing them more directly. So if we look at the late universe, this is some nice work on large-scale structure and mapping the overdensity and underdensity of neutrinos on the sky. This is only for high multipole moments, but it shows that there's sort of a multi-messenger aspect of neutrinos where when they transition to be non-relativistic after recombination, they kind of ride and fall into the overdensity and voids of the present universe. And so if we get to a stage where we can map the sky by using polarized targets to look for directionality of the capture count rates, then we can potentially, have an independent measure of the inflationary perturbations that's stretched out to scales of several hundred megaparsecs in our vicinity that would have an important footprint. In fact, the most important footprint would be on the dipole and the quadrupole moments, which, because of the cross-section times velocity being a constant, we are, sort of relatively insensitive to our motion with respect to the rest frame of their creation. We could, sort of verify this important aspect of the perturbation distribution in the current universe. So, however, the neutrinos are often considered to be impossible to detect. They don't interact very strongly, and then the most critical aspect that was looked at is the fact that their momentum is so small, a fraction of a milli-electron volt, which for non-relativistic neutrino, p squared over 2m would be a fraction of a micro-eV scales that we haven't conceived of experiments to measure those small kinetic energies at this time. But if we were able to take a process that had no energy threshold, which allowed us to at least capture the neutrinos. The current nuclei that we're focused on is the tritium, which has a 12.3 year half-life, and it has an endpoint of roughly 18.6 keV, still quite above the mass scale of the neutrino, but relatively low with respect to the scales at which measurements can be made. And we considered those as potentially a target in which we could capture neutrinos on tritium to produce a 2-to-2 process with helium-3 and electrons in the final state. Then if you do an analysis of the kinematics of this process, then you can see it sort of the left, the blue half of this plot is the energy of electrons in coming out from the beta decay of tritium. There's a sort of phase space effects depending on the finite mass of the antineutrino or the electron flavor component of the antineutrino eigenstates, where we don't know exactly what the absolute mass scale is of the neutrinos, and we don't know the ordering of the masses that come from the oscillation experiments, but we have sort of predictions on the order of 50 to 100 milli-electron volt of what the distortions would be on the beta decay spectrum. And in contrast, if you look at the capture cross-section on the right, you would have this 2-to-2 process where, again, the displacement of the capture peak would be varied based on the hierarchy and the absolute mass scale. And so this, original concept, which was proposed by Weinberg based on sort of the Pauli exclusion of the endpoint of tritium, was revised in the view of the finite neutrino masses to give us exactly this view that I show here by Coco, Mangano, and Messino. And so if we want to design an experiment that takes into account the finite neutrino mass that we know should exist from neutrino oscillations, and at the same time the constraints from precision cosmology, that where we know the sum of the neutrino masses has clear signature on the acoustical peaks and the current omega neutrino, that having experiment that has a resolutions comparable to neutrino mass and a dynamic range in the sub-eV range seems to be the right fit for the long-term development of relic neutrino experiment. At the same time, the many orders of magnitude between the left-hand side and the right-hand side indicates that we really do need to cut down the rate of neutrinos and have the resolution to make a sort of part per million measurement of the energy of the electron at the endpoint. The current state-of-the-art experiments, Katrin, are able to filter by better than 10 to the minus 4 on the endpoint of the spectrum. Ptolemy aims to sort of match that capability with a much more compact and albeit more complicated dynamical filter, but one that's can be scaled up by just replicating the number of filter devices. And then to add on to that, a 1% TES micro-calorimeter measurement that's measuring in this sort of few EV kinetic energy range. So if we look at the block diagram, we have a tritium target on the left, and we have a measurement of the few EV of kinetic energy of the remaining electron kinetic energy after it's moved up a very precise potential energy difference that's kept statically between the target and the calorimeter. And in that space in between, we implement a new type of filter, which is based on, firstly, the crest-based RF detection that was developed by Project 8, but implemented in sort of a uniquely different way, and a sort of transient tagging mechanism that allows us to trigger and configure a dynamical filter that allows us to efficiently transport electrons at the endpoint into the microcalorimeter for this differential energy measurement. So I'll talk about in this Ptolemy overview where we are with the different configurations, and most importantly, our demonstrator, which is coming together at the Gran Sasso. This is a magnet being made by ASG Supersys. It's 27 tons of iron with superconducting, conduction-cooled magnesium boron magnets. No longer, I say, in the category of tabletop experiments, but it shows you sort of that we're doing a demonstration of the end-to-end measurement precision with a target source region, an RF region in the center to run the sort of dynamical triggering information for a transverse drift filter that brings the electrons from high field into a low field region, as in fact a zero field region, which the TES microcalorimeters will reside to make that critical last step. So I'll focus mainly on the physics of the source and the calorimeter. My colleagues like to remind me that no matter what's happening in the middle, as long as I'm not perturbing the energy of the electrons, that it's really just sort of a transport mechanism between the target and the calorimeter. So if we focus on the finite phase space that comes in from having a neutrino, or in this case an anti-neutrino mass, the difficulty of being able to populate the endpoint of the spectrum is that typically you have to have a large amount of beta decaying material. So what we found when we were studying graphene, which is a nice room temperature stable method of holding weakly atomically bound tritium, still there is some fraction of the daughter helium-3 ions that are bound to the graphene. So it's a Mossbauer-like effect in which there's very little energy in the p squared over 2m from the mass recoil of the substrate, but the energy of the excited state takes away energy from the outgoing electron. And so each one of those excitations is a new threshold that has neutrino mass observables that turn on after that threshold. And since the degeneracy of the excitations is growing, the sort of the fractional feature of this mass observable continues to repeat across the spectrum. And we believe from our initial studies that this allows us to have substantially less tritium mass to get sensitivity to the absolute neutrino eigenstate values. And so we're making a great focus on doing into the demonstrator the production of tritium-loaded graphene samples in which we can try to make an absolute neutrino mass by looking at the quantum excitations of the daughter particles on the graphene. Let me tell you a little bit about the measurement side. We have the world's best microcalorimeters for EV scale energy measurements. On the bottom right is first one is pedestal, but then the next one's a 1.8 EV infrared photon 2, 3, and each one is measured with 10% resolution. We're not just counting neutrinos here; we're measuring the energy, or I'm counting infrared photons, measuring their energies with great precision. We've managed to scale up these the area of these devices. They're very thin. They're on order, I don't know if it's written here, but on order 40 nanometer of material, which is all that is needed to stop electrons or infrared photons at those energy scales. We're trying to make we have a device that's already built that has a larger energy range, 100 EV, to allow us to test with the demonstrator. It's a bit nonlinear in its response, but it already can count infrared photons out to an amazing distance. We have new method of irradiating that device with low energy electrons. We actually use carbon nanotubes and field emission, and those measurements are ongoing. So we also have great development, a recent paper on how to detect the electrons in the RF region. The electrons are drifting slowly through the RF region. We can hold them in place for roughly 10 microseconds to get enough signal to noise. And we use a kind of a template method that allows us to infer what their bouncing frequency is and the pitch angle, and therefore configure our new type of filter in order to do a velocity or total energy selection on them. So our filter, the way it works is to look at the drift of the cyclotron motion of the electron as it goes through a magnetic field gradient with an E cross B drift term keeping them on track. And so it's a unique type of filter, but it's sort of relatively straightforward once we have it working well. We have a new device that's being able to load tritium on graphene with very high efficiency, over 90%. It's tested with light hydrogen, but we're hoping to move it to Karlsruhe to use this for tritium loading. We also have designs for large area targets to be able to eventually scale up way beyond what we're doing now with many spectrometers, so that we can have sensitivity to the relic neutrino mass. Right now, we're focusing on areas that would give us roughly a couple hundred micrograms of tritium to make the neutrino mass measurement. In recent workshops, the technologies Ptolemy is trying to bring together are actually all of interest to all the community in Project 8, Katrin, Holmes, Echo. So we have really a kind of a vibrant community that's looking at all these different aspects. Ultimately, these uncertainties of the absolute neutrino mass and the resolutions that we have for both for the target and for the measurement system are critical. This is a plot, Dirac neutrinos, Majorana neutrinos on the left and the right. This is for relatively low spectrometer resolution. And this is what we would have in our target resolution. So we would be able to cover the standard prediction for the neutrino rate. And so our goal is to be able to get there so we have a long-term future.